The moment you've all been waiting for. The basketball match that decides who is the top dog, who will take the crown as the king, and who will bow down to the new leader. I now present to you Athan Moreira versus Max Fraser.
For my theme song, my leather black jeans on, my by any means on, part and I'm getting my scream on. Into the kingdom, but watch it you bring home. You see a black man with a white woman at the top floor, they gon' come to kill King Kong. Middle America packed in, came to see me in my black skin. Number one question they asking, what the question you asking? If I don't get ran at my Catholics, it goes to conservative Baptists, claiming I'm overreacting like the black kids in Chirac. 4 in the morning, and I'm zoning, they say I'm possessed. It's the omen, I keep it 300, like the Romans, 300. Where the Trojans, baby, we living in the moment. I've been a menace for the longest, but I ain't finished. I'm devoted, and you know it, and you know it. So follow me up, cause this about to go. I'm doing 500, I'm out of control, but there's nowhere to go, and there's no way to slow. If I knew what I knew in the past, I would have been like that on your.
Let's now take a look at why Athan lost because of his incredibly bad jump shot.
After we have put our points into the video tracking software, we get a graph like the one in front of you with all the different points following the trajectory of the ball. If we put that graph on a grid, we can kind of better see the proportions of where exactly these measurements are, and it begins to be more reminiscent of graphs we'd be more used to finding the velocity of in class. If we take away the gym, Athan, Max, and everything else, we can get a much better sense of exactly what the ball was doing as it traveled across the different arcs. So as we can see, the ball took 3 different arcs, so 1, 2, 3, and bounced 2 times. It finished here, started here. There you can see the seconds, so the time at which the first bounce happened. There's the time at which the second and final bounce happened. There is the split in between arc 1, arc 2, and arc 3. There is the time, obviously, 0 seconds at which it started. And there is the time at which it finished. So the total time it took for the ball to complete all 3 bounces. And we stopped recording at 3 bounces, therefore our points don't really go past there. Now this is showing the displacement value, so the x value in meters for the different events in the arc. So as you can see right there, that's the displacement at the first bounce. That right there is the displacement at the second bounce. That is the displacement at the first data point we recorded. So this is where, even though it's not where the ball started in its arc, because of the limitations in the video software, as Jack will discuss later, this is where we started recording. And this is the value, the displacement value for when the ball finished its 3 arcs and finished its total trajectory, and we stopped counting the arc, stopped keeping track of the arc of the ball. So to find the equations of the line, we took the values that we got, the points that you'd just seen on those different graphs, and we put them into Desmos, like you can see right there. As you can see, there was quite a few of those values, but we put them into Desmos, and it looks something like that. So as you can see, there is arc 1, arc 2, and arc 3. And then with the graph here, with the scale on the graph, we can look at it, we can find out all sorts of different important points, like the max. We can look and we can find the start and the finish of each individual bounce, and this will be important setting the bounds later of our equation. And yeah, okay, so in Desmos, we took each one of our graphs, each one of our arcs that the ball took in its trajectory, so all three, the big one, the medium one, and the small. And we used this standard equation here, so we plugged that into Desmos as a template of sorts, and then Desmos gave us back these three values here, which correspond with the different variables in the standard equation. And then we did the same thing with the same standard equation for this one, and got three different values, and for that one, and got three different values. And what's happening here is Desmos is taking a line that follows this equation and trying to best to fit it to the data that we had in our experiment. So if you look at it, we really don't know just by looking at the graph if it's actually the best fit, because Desmos just does an approximation. So we can look at this value right here, the r squared value, that's called the coefficient of determination. And the closer that r squared value is to 1, the more accurate the graph Desmos has provided. So the better the graph Desmos has provided fits the data in real life. This is because, as you might imagine, the data is not it's not a perfect curve. There are some variations in the points, so a normal curve won't fit it perfectly, but as you can see, all of our values are pretty close to 1, so we got quite close enough to have a high level of confidence in the results that Desmos gave us. So as you can see, this formula here corresponds with arc 1, this one with arc 2, and this one with arc 3. And now if we take the numbers that Desmos has given us, we can plug those numbers back into the template equation, the one that we got over here, and that will give us the actual equation of the line that we'll be able to use in a mathematical sense. So we can do the same thing that I just did for the first one, the next two, just taking the values that we got from Desmos and inputting them in to the corresponding variables in this template equation here. Okay, so the goal of this whole experiment was to find the velocity, and typically velocity is calculated as distance over time. But because we are looking at a ball with an arcing trajectory, we have to use what's called arc length. So arc length is basically the length of the curve. So by taking the length of the curve, we can find the distance traveled of the ball as it moves in the x and y direction. Then we can take that distance traveled and divide it by time in order to find our velocity. Now to actually find the arc length, we use this formula. This formula is called an arc length formula. A few important things to note here. These bounds here, A and B, they are representative of the x value at which the curve starts. So earlier on, those were labeled on the graph, and those labeled values, the x values in meters, will be used to fill the bounds. So A here will be the start, and B here will be the end. So the graph will go from, if the curve goes from, let's say, 1 to 7, the A bound will be 1 and the B bound will be 7. Okay, and then when we are using our formulas that we just figured out in Desmos, we'll actually take the derivative of them and plug them into this dy dx portion of the formula over here. So that's where the formulas from Desmos will go, and then the bounds from the starts and stops, the displacement values, the in meters will go over here with in the bound section.
Now for the math part of the video. Here for arc 1, we have our arc length formula and the equation we got from Desmos. First step is we take the derivative of that equation. Then we sub the derivative value into there, replacing the dy over dx portion of the formula. After that, we take the bounds. These are the stops and the starts for the different bounces. B would go with the B bound, A would match up with the A bound. Once you have both the bounds, you can compute your equation in your calculator, and you will get approximately 10.87 as your arc length.
Then going back to the graph, we can find out that it took approximately 1.9 seconds for the ball to take its first arc. So using our velocity formula as we looked at earlier, we can sub in those numbers here and here, and we can get our velocity for the first arc. For the second arc here, we have the same arc length formula as earlier, our new equation from Desmos, so our different derivative this time, and then we go down here, we sub the derivative in for the dy dx portion right there, and then we connect the bounds, so that bound goes there, a bound goes in the a bound spot, and the b bound goes in there. So these are different starts and stops because this is the second arc, so the second arc stops where the first arc left off, and then it'll continue that pattern with the third arc. So if you take this with the bounds and the new derivative plugged into the dy dx portion of the formula, you get approximately 5.268 meters as your arc length. So then to find the time, it's a little more complicated. You have to take the time at which the arc 2 finished and subtract that from the time when it started. So that looks like that right there. And then that gives you that value, approximately 1.43 seconds. Okay, so then you can take that, you can take those numbers, you can bring them back to the velocity formula. You can plug that in, meters on the top, time on the bottom, and you get the velocity for the second arc. Okay, then for the third arc, it's obviously more or less the same. You have the arc length right there, that formula. You have the new equation that we got from Desmos. Then you have the derivative of that equation that you took. That was your first step. And then this, like the others, your second step is to plug that in to right there, dy dx portion. Then you connect your bounds. Now, once you've connected your bounds, you plug all that into your computer, bounds and dy dx, and you get your final answer right there, final arc length value. So you do the same thing as the last one to find the time. You know that the time, like the bounds up there, the time stops where the last one, starts rather, where the last one ended off. And in this case, because it's the third and final, finishes at the end of our data points. So that time there is the last recorded time we have in our data points, because we finished our data points at the end of the third arc. So then you do the same thing here, you plug those values in, meters over seconds, and you get the velocity for our third and final arc.
So, in terms of potential shortcomings, there are a few ideas we should discuss. The first is that the grid is based on the plane that the basketball is shot in. So this means that after Athan shoots the ball and he walks off of that plane, it looks to be distorted. Now, despite this potentially confusing visual, the data is still accurate as the ball is on the same plane, so we would expect to see the data still be accurate. Next, the ball might not have been inflated to the same PSI as is standard in league basketball, so this might create some differences in how we would expect the ball in an actual game to bounce versus how the ball bounced in our video. Next is that always the potential for human error, especially in the software and the selection of data points. When we were selecting our points, we could have potentially misclicked on the area of the ball. And then finally, Athan's arc was far higher than a standard shot would be, so this would create some differences in what we would expect to see the next bounce be, but it should still scale proportionally.